So the next section is we're going to look at VASP performance on Perlmutter and just some metrics that have been used to measure this. So first, VASP is a major production code in NERSC. It has one of the highest user bases of any individual code running on Perlmutter, and it uses over 15% of NERSC computing cycles each year, and is one of more than 900 codes that run at NERSC, but it has a substantial piece of the pie. As of April 15th, when I last checked, I noticed there are about 849 active VASP users on Perlmutter, and that number keeps growing. So VASP, as far as especially its GPU ports, has been a subject of considerable effort. So previously, it was a tier 2 NESAP application in previous NESAP cycles, and NERSC and NVIDIA worked together to help the VASP Corporation with this open ACC porting. So a lot of work has been going into that, into making it performant especially on GPU nodes. And we'll also mention that all the major paths are in GPUs except for things involving random phase approximation, such as GW calculation and adiabatic connection, fluctuation dissipation theorem jobs. One more thing to mention is that we are regularly updating the software environment of Perlmutter. And so the performance that you get for an individual job is can change from maintenance to maintenance. So in this table, we have 6 representative benchmark systems that have been used to test VASP, which use different code paths and have different sizes. The PD04, CUC VDW, and SI256 HSE are larger systems, which are more likely to get performance benefit running on GPUs, and the remaining systems are smaller. Also, PD04 and PD02 are the same type of workloads, and they only differ in size. The Silicon 256 HFSE system and BHR105 HSE are doing the same kind of HSE hybrid functional calculation, but they're just using different sizes and elements. And the main thing that I want to draw your attention to is in this table, the differences in numbers of electrons, functionals, bands, FFT grids, and K-points. So this table is representative of a large variety of VASP workloads that one might have. In this slide, we're going to look at one particular system, Silicon 256 HSC, which is a 256 atom silicon supercell that has a vacancy. And this is an HSC hybrid functional calculation, which is one of the most important workloads available in VASP. What you can see in the graph is if you compare Perlmutter with the previous systems, Corey Haswell, we have normalized to being a 1 in terms of speed up. And the system before that, Edison, is about 70% as fast as Haswell for this particular job. And then Corey K and L is 1.6 times as fast. Looking at Perlmutter in comparison to these, you can see that even just using a fourth of a Perlmutter GPU node gives you an 8 times speed up compared to the Haswell job. And if you run on a single Perlmutter node with all 4 GPUs, you get a 31 times speed up. And then if you increase the number of GPU nodes, you can even get speed ups of up to 141 times. And if you compare this running on 16 nodes with 64 GPUs with a 16 node calculation on the other systems, you can see there's a substantial speed up for this job compared to running this on the earlier systems. If you look at the other 5 benchmarks and their performance on Perlmutter compared to Corey Haswell, Corey K and L, and then a single versus multiple node comparison, you can see that Perlmutter gives substantial improvements for these workloads as well. We didn't show the original system, the Silicon 256 HSE here, because it's off the charts. It's on the scale of this graph. One thing to note is that because these workloads are smaller than the Silicon 256, they get less performance boost from using GPUs. And you can see from the chart that for the single node performance, Perlmutter performs about 7 to 9 times faster with larger benchmarks and a smaller HSE benchmark, and about 4 to 5 times faster for the last relatively smaller benchmarks. Also, if you look at comparing the multiple node-to-node performance comparisons, Perlmutter performs about 6 to 8 times faster than Corey Haswell for the first 3 test cases and 3 to 4 times faster for the last 2 smaller test cases. And finally, if you compare the performance of Perlmutter GPU nodes with Perlmutter CPU nodes, then you can see that in this case, Perlmutter GPU is running on 4 MPI ranks and 4 GPUs, whereas Perlmutter CPU is running on 128 MPI ranks. And you can see that the speedups are 2 to 9 times, with the GPU being 2 to 9 times faster than the CPU nodes, depending on your system. So with that, for your own jobs, these are there are several tips that I have for maximizing performance. The first is to guess nothing and measure everything. And by this quote, I mean, if you intend to run production calculations, particularly if you have many, many runs to perform, we recommend that you first do a systematic test to figure out the best parallel configuration that gives you the best performance to cost ratio for your system of interest. And the VASP wiki also has some advice, which I've distilled on a part of that onto this slide. The first thing we generally recommend, as shown by the previous slides, is that use a GPU build if your application allows. There's some applications which run only on CPUs because they use a plugin. Or if you don't have GPU hours, then you would run VASP on a CPU node. But if you use GPU builds, this gives you generally the best performance. The other thing is VASP is constantly being improved. And so using the newest version of VASP that's allowed by your license that's installed on Perlmutter is a key to getting the best performance. A couple other points is, as I mentioned earlier, avoid running on hyperthreads, as this is very bad for performance. And then also, if you are running a CPU build, you have the option of using either in-core parallelism, which is declared in your in-car file, where you can set in-core to be equal to something like 4, 8, or 16. Or instead of using in-core parallelism, you can use OpenMP threads, but you can't use both of these at the same time. So for CPU jobs, I recommend that you try several different values of in-core and several different values of OpenMP threads, and then compare the performance of your test job with all of them to find the settings that give you the best performance. And lastly, if you're running a job with multiple K points, you can set the K-par to factor the irreducible K points, and you can get performance benefits doing that. And that works in both CPU and GPU builds. But keep in mind that that also increases the amount of memory in your calculation. So if you have to adjust the amount of resources to do this, then just be aware of that.